Hello, everybody.
Professor.
Got another minute or two here. Wait for everybody to join us. Okay, so welcome. Tonight, what I hope to achieve tonight is we're going to finish our presentation on deflections, serviceability, cracking, and deflections. We had left off, we had covered instantaneous. If somebody could please mute. So where we had left off last time is we were talking about instantaneous deflections. And tonight we're going to wrap it up by covering long-term deflections. And then I'm sure there'll be plenty of time after I finish tonight's presentation, we can talk about the midterm. But let's get through the presentation first, and then I will be more than happy to answer questions regarding the midterm, and including going over instructions on how to take the midterm. So without further ado, unless I will start the time off though, if anybody has questions about their homework that they would like to ask first, not the midterm, because I'll cover that for everybody at the same time, but any questions about homework?
I have a question.
Sure.
For homework problem number 3.
Homework.
Our homework for problem number 3.
Okay. Yeah. Okay, I got it.
So when we're given a problem like this, is what's signaling that we design for a T-beam as opposed to the one-way slab, is what giving that impression? Sorry, I'm not wording that great, but is the 24-foot simple span what telling us that we designed for the T-beam and not for the one-way slab? That
yes.
makes sense.
Yeah,
Okay.
yeah. I can see that it might be a little confusing. Am I asking for the one-way slab or am I asking for the beam? And it is the beam. Some of your tip-offs are that I gave you 24-foot simple span, that the rebar is shown as 3 number 9s. The rebar is going in and out of the page at the bottom of the beam. So that would do absolutely nothing for the one-way slab design. And the D is given to you as 29.5 from the top of the concrete to the center of the 3 number 9s. So yeah, all of that together is what would steer you away from the one-way slab. And I would be more specific. I would say, please design one-way slab, and I would give you like no information on the beams. So
okay. And for part B, when you want us to design using MU equals 800.
Yes.
And then you want us to find the area of steel required.
Yes.
So the first thing I did was I got my rho, and then when I tried to plug it into rho BD, I used one of your examples from lecture 5 as like a reference. And you plug in the effective width for B there. I wasn't sure like if I should plug in the BF value or the BW value there.
for, what are you trying to solve for? Little a or for the minimum steel?
I'm trying to solve for the area of the steel required using the rho BD equation.
Okay. Well, then that would be the effective flange width.
Can you kind of explain why it would be like what would tip us off that it's the flange width that we use as opposed to the web?
The web would only be used for minimum steel. And you use the web for minimum steel because minimum steel is based off of having enough steel that when it cracks, it won't fail. So
Okay.
that's the only time really that you're using the web is for your AS minimum steel, that equation, which is 3 square root F prime C over Fy BWD. That BW is the width of the web. The
Right.
effective flange is the only part of the whole beam that's in compression. So that's the only one that really matters to the design of the beam.
Okay. That was the only part I was kind of not sure what to do.
Okay.
And then when I used the table A5 to check the minimum width if it's satisfied.
Uh-huh.
And
Yes.
right there, I would compare with the 14-inch of the web as opposed to the 62-inch effective width.
Well, absolutely, because your steel
Yeah.
has to fit inside the web.
Right. Okay. Even though it's a rectangular, we're treating it as a rectangular beam.
It's
In real,
behaving as a rectangular beam, but you can't put your number 9 bars floating out in space. They have to fit inside the concrete.
so you still have to consider the web width there, no matter what.
For the practical constraints of building it, yes.
Right.
But for
Okay.
the design, the normal concrete design, part of the concrete is compression and all the rest of the concrete is cracked. So as far as the beam is concerned, it doesn't exist.
Okay. That makes
So,
Okay.
sense.
Professor,
Yes.
so you use the effective flange width in the equation for A, correct?
Yes.
Okay.
Unless you find that the A that you get from that is larger than the flange thickness, in which case then you have to design it as a true T-beam. And then you got to follow the procedures that we went through in the lecture about how to do that as a true T-beam.
Okay.
And Professor, when you solve for E sub T and it's only a single layer of steel,
Yes.
you use the depth to the center of that single layer of steel, right?
Yes.
As opposed to if it was 2 layers, you use the depth to the bottom of the lowest steel, right? Is that correct?
You use the depth to the center of the lowest row.
Oh, okay. I
Yes.
thought it was to the very bottom in one example we did, but I'll have to go back and
Yeah, it's probably just the way I drew it, but it's,
okay.
you have D. D is always from the top of the concrete to the center of all of your steel. D sub T is from the top of concrete to the center of your lowest row of steel. If you only have one row of steel, then D sub T and D are one and the same. But if you
Right.
have multiple rows, then they are different.
Got it. Thank you.
You're welcome. Okay, Anthony, can we solve problem 3 using a similar method to example 5.4, page 118? I have no idea. Let's see. Page 118. Oh yeah, that looks kind of similar, doesn't it? And so you assume 0.9 VM, assume a lever arm, 0.9. Oh, okay. Yeah, I guess you could do that. I didn't do it that way. I don't really like that way, but you could do it that way. The proof in this is in the pudding. So when you get to page 119, you're going to calculate a value of little a, and that little a is either going to be thicker than the flange or it's going to be less than the flange. And that will tell you if it's rectangular or true T-beam. And then once you know that it's rectangular or true T-beam, then the rest of the problem, starting with checking minimum reinforcement, computing C, epsilon T, and phi, looks like that's the end of the problem. All of that is going to be the same, but you don't really know. The question has not been answered. I want to make sure everybody understands this. The question has not been answered if you have not calculated phi mn greater than mu. That's the proof of the pudding. So however you get to an estimate for how much steel you need, or an estimate to how deep the beam needs to be and how much steel you need, those are all just tools and techniques to get to some point. But once you get to that point, it is AS minimum satisfied? Is epsilon sub t less than 0.0 or greater than 0.005? And is phi mn greater than mu? Those are the questions you have to answer on every single problem. And then you know. So yes, you can use their technique. It's a little different than my technique, but it gets you to the same spot, if that makes sense. Okay, so let's start with long-term deflections. If everybody remembers, we covered in our last discussion, we talked about instantaneous deflections. And instantaneous deflections required us to calculate m cracked, and ma is the applied moment, and the gross moment of inertia and the cracked moment of inertia. And then we plugged those into the Branson equation, where we took ma over m cracked to the third times I gross plus 1 minus ma over m cracked to the third times I cracked. And then we found our deflections. Continuing from that, we will now start talking about long-term deflections and what is the difference. So deflections found in the previous section were instantaneous or happened nearly immediately after the application of load. Because of the effects of creep, instantaneous deflections will continue to grow over time if that load is sustained. So here's a chart that shows this is time and this is strain, compressive strain due to a load. So if I apply the same load at day 1 or day 4 or day 7 or day 14, in every case, the strain immediately due to the load is virtually the same. So it immediately jumps up to a compressive strain basically on how we calculated stress and strain using gross moment of inertia, chapter 2 stuff. So it immediately strains due to the load, but because of the effect of squeezing concrete is actually squeezing water out of concrete, you get a continued strain, an increase in strain over time. And that increase in strain is much more severe the younger the concrete is, because the younger the concrete is, the more water it still has in its matrix. So what this is illustrating is the same load applied on day 1. If this strain is, this is 1, so this is like 0.001, this would be 0.005 immediately, but it's going to grow over time until eventually it basically peters out into a long-term deflection. But this long-term deflection is many times greater than the immediate deflection, like almost 4 times as great. If I apply the load at day 14, the effect is roughly half of the total deflection that I got from loading it from day 1. So this is just a illustration of the effects of creep. The longer you can wait to load the structure, the less severe this long-term effect is going to be. So the two effects of time and loading The age of concrete when first loaded has a dramatic effect on the total long-term strain. And creep is greatly increased if the member is loaded early, 7 to 10 days, as opposed to 2 to 3 months. However, this effect is not addressed by ACI 318. This whole thing, there's no calculating factors for that in the code. And the duration of the sustained load. The longer a load is sustained on the structure, the greater the creep strain will be. ACI 318, section 242413 points to table 242413 for a psi factor, hopefully I'm saying that right, psi factor, for different load durations. Generally, psi equal to 2 will be used for loads lasting longer than 5 years, which generally speaking is most dead load. Most of us design concrete buildings assuming they're going to be in service longer than 5 years. So we just use a psi of 2. After about 5 years, these slopes basically flatten out and you don't really get any additional deflection after about 5 years. Sustained loads may include some of the live load. Code does not mandate this, but is left to engineering judgment. Sustained loads may be assumed to be all the dead load plus 20 to 25% of the live load for offices and residential, or it may be assumed all the dead load plus 70 to 80% of the live load for warehouses. So think of like a typical office. How much of the live load is you and me going in and out of the office every day, and how much of the live load is bookshelves and file cabinets and tables and furniture and that sort of thing, as opposed to a warehouse. A warehouse, basically everything you load into a warehouse is considered live load, but at any given time, you know, go visit an Amazon warehouse at any given time, 70–80% of it may be fully loaded all the time, which is pulling down your structure. Any questions so far? Okay. Compression steel will mitigate some of the effects of creep. As the concrete creeps, the additional strain is arrested by the stiffness of the compression steel. Steel does not creep. And remember, one of our fundamental assumptions is that whatever the concrete's doing, the steel is going to do the same thing in terms of strain. So if the concrete is trying to increase the strain, the steel's not going to let it. The steel's not just going to go along for a ride. So steel does a great job of arresting creep due to concrete. ACI section 242411 addresses this with equation 242411, where lambda delta is equal to psi over 1 plus 50 rho prime, where psi is from table 242413, rho prime is AS prime over BWD, as calculated at midspan for simply supported and continuous beams, and at the supports for cantilever beams per ACI 318 242412. Therefore, the total deflection delta total is the sum of the instantaneous and long-term deflections. Delta total is equal to delta instantaneous plus this lambda delta, this factor here, times delta sustained. Okay, so as an example, I got a beam.
I'm sorry, Professor. Can you just for 1 second go back to the previous slide?
Of course.
Thank you.
Did you have any questions, or you just needed to get caught up?
I just needed to write down that the rho prime.
Okay. Okay. You got it all?
Yes.
Okay, great. Okay, so example 3, we're going to look at a beam that's 27 deep, 20 inches wide. I got 6 number 8s on the bottom. I got 2 number 8s as compression steel. It is 4,000 PSI concrete, 60 KSI steel, flexural reinforcement, 6 number 8s, compression reinforcement, 2 number 8s. My dead load is 1 kip per foot, including the self-weight. I'm sorry, not including self-weight. Live load is 1.5 kips per lineal foot. Span is 36 feet. Assume simply supported. And what I'm requiring is find the long-term at 5 years deflection for the beam and assume that 20% of the live load is sustained. Solution. I gross, BH cubed over 12, 20 times 27 to the third over 12. And notice that I gross is based on the gross section. You're not using D in here, you're using the gross section with 27. That gives us 32,805 inches to the fourth. Modulus of rupture is minus 7.5 lambda square root F prime C. Plug in lambda 1 and 4,000. I get minus 474 PSI. And so we find our cracked moment of inertia. Now, remember, I think we went over this before. Remember that you have the transformed area of your flexural steel is your modular ratio times the area of steel. Your transformed area of compression steel, however, is 2 times, because of the creep strain, psi is equal to 2. So that means the steel is going to be picking up 2 times its stress, and minus 1 because the steel is actually creating a hole in the concrete. So 2n minus 1 times your compression steel. M cracked is the modulus of rupture, I gross over y sub t. Plug those in, I get 1152 kip inch or 96 kip feet per M cracked. E modulus of elasticity, 57,000 times 4,000 is 3605 KSI. Steel is always 29,000. Modular ratio is 29,000 over 3605, 8.04. Area of steel, 6 times 0.79 from your text, 4.74 inches squared. My compression steel is, my transformed area of steel is N times AS, 804 times 4.74, 38.11 inches squared. My compression steel is 2 times 0.79, 1.58 inches squared. My transformed is 2 times the modular ratio minus 1, and that's 23.83 inches squared. So I equate the first moments. That was the diagram I showed on the last slide. So the concrete is B times X wide times X over 2 is the moment arm. The compression steel is the area times X minus D prime is the moment arm, is equal to the flexural side. Oh, I'm sorry, no, that's not the flexural side. I'm just condensing this to this, plugging in the numbers. 20 inches X squared over 2, 23.83 inches squared, X minus 2.5. And all of this equals the flexural, or the tension side, is the transformed area of steel times D minus X is the moment arm. And I plug in my 38.11, 24.5 inches minus X, and I get a quadratic. 10x squared plus 61.94x minus 993.27 equals 0. Solving, you get 2 roots, one's negative, one's positive. Positive root is 7.34 inches. So I find my center of gravity, and this looks kind of nasty, but it's just the width of the concrete, the depth of the concrete, times the height from the bottom, plus the compression steel times the height from the bottom, plus the tension steel times the height from the bottom, divided by the total area. I get 19.66 inches. Or I could do it the easier way, 27 inches minus X gets me to the neutral axis, 19.66 inches. These two should be the same. And so I find my cracked moment of inertia, BH cubed over 12 plus the parallel axis, which is BH times the distance to the neutral axis squared, plus the compression steel times the distance to the neutral axis squared, plus the tension steel times the distance to the neutral axis squared, 14,417 inches to the fourth. Okay, do I have any questions about the geometry, the section properties?
If you want to do the if you want to calculate y bar from the top, you can do that, correct?
Yes, yes, you could. It might be a little confusing though, but that's a great question. Yes, you can.
For homework number 4, there was a T-beam, I think it was problem number 2, where the centroid was actually below the flange. So we were supposed to calculate the distance, or the distance to the neutral axis. And I used one of the examples in the book, and they also used a reference from the top of the T-beam.
Okay, you lost me a little bit. Which homework?
Homework number 4.
Okay, and which problem?
I think it was problem number 2, where the neutral axis was below the flange.
Okay, well, I'm very glad you asked that question because that's a completely different thing.
Oh,
But don't get discouraged. I'm very glad you asked that question. But that
okay.
is a totally different thing. Let me try to explain.
Please.
What homework number 4, problem number 2, you are looking at the ultimate state. You're looking at when the concrete is at 003, the beam is cracked, massively cracked, and what you're solving for is A, little a. Little a, it is the neutral axis, sort of. Actually, the neutral axis is at little c, not little a. But how do I describe this? That's the ultimate state. And if little a is below the bottom of the flange, then it's a true T-beam behavior. If little
Correct.
a is into the flange, then it's rectangular beam behavior.
Correct.
Okay, but all of that, homework number 4 in its entirety is limit state. All of that is where your concrete is just about to crush, your rebar is completely yielded, and your beam is on the verge of collapse. That's a totally different procedure than what I'm doing on the screen here. What I'm doing on the screen is a serviceability check. The concrete is nowhere near crushing. The rebar is nowhere near yielding. The beam has just cracked. Do you see the distinction?
Yes, I do. So, what does the y sub b represent in this case?
It is the distance to the neutral axis.
Okay.
It is. But the difference is, in homework 4, you're
It's already
assuming
yielding, right? It's to be cracked, correct?
yeah, the beam has long since cracked.
And this one, it's barely cracking, and that's
right. That's
okay.
right. But the big difference is that this one is assuming that your materials are still acting elastically. So if I were to look at like a section through here, let me annotate this. And again, I'm very glad you asked the question. If I cut a section right through there and I look at it from the side, like over here, then the stress in the concrete looks like this. and there's the neutral axis, and the stress in the steel is like down here someplace. As opposed to homework number 4, the neutral axis has shifted way up here, and the stress in the concrete assumes to be something like this because it's the Whitney stress block.
Correct.
So this is, and the rebar is completely yielded. So this neutral axis is totally different than this neutral axis. As the beam continues to crack and strain, the neutral axis raises up. It rises up.
Oh, that makes a lot of sense. That
Good,
makes
good.
perfect sense. Okay.
Yeah,
Thank you for clarifying that.
no problem. Thank you for asking. So this is the plastic state. This is the homework that you're doing. This is an elastic state that we're assuming for deflections. So the lecture is on serviceability. We're not factoring our loads. We're looking at the real loads, and we're trying to calculate deflections. But homework number 4 is calculating total strength just before the whole thing falls apart.
Okay. Thank you so much, Professor.
Okay, thank you. Okay, so where were we? Okay, so yeah, I'm glad you asked that. So we're finding the moment of inertia where the beam is still elastic and it has just cracked. We're considering that it just started cracking and it found a new balance between the concrete in compression, the steel in compression, and the steel in tension. Okay, so we were down here solving for our first moments. Okay, so why B? Oh, now the question makes a lot more sense. Okay, little c is the distance from the top of the beam to the neutral axis, but little c is always assumed to be as the beam is failing. Y sub b is from the bottom of the beam to the neutral axis when everything's still working elastically. Okay, so we got our gross moment of inertia, we got our cracked moment of inertia, and now we can move to our loads. Now notice the loads, we're not going to factor the loads. For serviceability, we do not factor our loads. So I have the 1 kips per foot that was given and the self-weight. The self-weight is the dimensions of the beam times 150 PCF divided by 144 to give me 1.563 kips per lineal foot. Again, I will tell you in a problem, if I don't say nothing, if I just say the dead load's 1 kip per foot, assume that the self-weight is already in there. But if I tell you 1 kip per foot, not including self-weight, then go ahead and do this quick little calc right here to add the self-weight to it. My dead load moment is WL squared over 8 because it's a simply supported beam. So 1.563, 36 squared over 8, 253.2 kip feet. My live load, again, simply supported, so WL squared over 8, 1.5, 36 squared over 8, 243. So first we want the deflection delta due to the dead load only. Therefore, MA is equal to the dead load moment. Again, remember we talked about M sub A is the moment at whatever load stage that you're trying to calculate. So if we just want the deflection due to dead load, MA is equal to the dead load moment. 253.2. M cracked over MA, we calculated M cracked was 96 over 253.379. We use the Branson equation. I plug in my 0.379 here and here, my gross moment of inertia here, my cracked moment of inertia here. My effective moment of inertia is 15,418.
Professor?
Yes.
Okay. Every time we do when we calculate our own dead load for the 150 PSF, I confuse it with the homework number 3 because you gave us a live load of 150 PSF. However, in here, you're using a dead load of kips per linear feet.
Yes.
Why is it that for one-way slab we use PSF, and for beam we use kip per linear feet?
That is the law of nature. When you,
Okay.
no, it really is. It's just kind of how we do it. But it comes from anytime that you have an area would be like the one bay. So say like your columns are 30 feet apart by 40 feet apart. So your bay is 30 feet times 40 feet. The loading in any particular area is always given as pounds per square foot. Live loads are almost always given in pounds per square foot. Your house is 40 pounds a square foot. Parking garage is 40 pounds a square foot. Egress is 100 pounds a square foot. Light storage is 125. Heavy storage is 250. Most of your given loads are pounds per square foot. So anytime you're designing an area, you use pounds per square foot. And so slabs cover an area. They go from here to there and from over here to over there. Slabs are designed as pounds per square foot. Normally what you do in everyday design is you design your slabs first, and your slabs are spanning from beam to beam. So when you design your slabs, you're designing with pounds per square foot. But when you take the tributary area of your slabs, then the loads to your beams are pounds per square foot times the tributary width. That gives you pounds per lineal foot or kips per lineal foot. So normally we design beams for kips per lineal foot because we really don't care what's framing into it. We already designed that. Now we're just trying to design the beam. So we use kips per lineal foot. Likewise, when beams are being supported by columns, by the time you get to the column, you're designing for kips. The reaction of the beam becomes the load on the column. So it's a load path. You're going from a big area to a line to a point.
Okay, but whenever we're doing our moment, for example, you did it right there, it's the 1.563 kip per linear foot times the 36 feet squared. But if we're using PSF, or for example, KSF, will our moment units be wrong?
No, that's where it gets a little wonky. If you're designing a slab, everything's in pounds per square foot. But when you run pounds per square foot, you design a slab for a 1 foot width, remember? So pounds per
Okay.
square foot on a slab really is pounds per lineal foot because you're only looking at a 12-inch wide piece of slab.
Okay, thank you for that. Now everything clicks. Thank you.
Perfect. Okay. Okay, so we were here, our deflections due to dead load. The equation for deflection of a simply supported beam is 5W L to the fourth over 384 EI. That comes from a table. And so I can plug in my numbers. And I've got, now, again, I mentioned this last time, I'll mention it again. Watch out for your units. The load is kips per lineal foot. The span is feet. But your moment of inertia is inches to the fourth, and your modulus is kips per square inch. You can't do an equation with feet and inches. So we put 12 to the third inches per foot, cancels out the feet, and now everything's in inches. And we get 1.063 inches deflection. This is instantaneous deflection due to the dead load. Next, we want the deflection due to dead load and live load. Therefore, we calculate what M sub A is the moment of the dead plus the moment live. 253.2 plus 243 is 496.2. For 96 divided by 496 is 0.193. So I use the Branson equation. I plug in the 0.193 here and here. Gross mole of inertia, cracked mole of inertia, and the effective moment of inertia is 14,757. My applied load is the dead load plus the live load. So that's 3.063 together. And I calculate my total deflection. I plug in my total load, span, my inches to feet, and my effective moment of inertia. And I get 2.176 inches. If I find the live load, you can only find the live load by subtracting the dead load out of the total load. You can't calculate the live load directly because of these factors, but you can calculate the total load and then take away from that the dead load. What you have left over is the live load. So live load is the total load minus the dead load, 2.176 minus 1.063. 1.113 inches. Now, with the instantaneous deflections found, we can now find the long-term deflection. So rho prime is AS prime over BWD, 1.58 over 20 and 24.5. And remember, rho prime is AS prime over BWD, not D prime. That'd be an easy mistake to make. So the rho prime is 0.0322. Psi from the table is 2 for 5 years. So lambda delta is psi over 1 plus 50 rho prime, which is 2 over 1 plus 50, 0.0322. And lambda prime is 1.723. See, the difference that the compression steel made is lambda prime would have been just 2 if you had no compression steel. So 2 to 1.7, something like a 15% reduction in deflection because of the compression steel. And so delta sustained equals 1.063 dead load plus 20% of the live load, because we defined in our problem statement that 20% of the live load is sustained. That equals 1.286 inches. So delta total is your delta instantaneous plus your lambda delta times delta sustained, which is 2.176 plus your 1.723 times the 1.286 sustained, for a grand total of 4.39 inches of deflection. Does that sound good? 4.3 inches of deflection? Would anybody be happy with that in their house? Sounds like a lot. To me, it sounds like your piano is going to keep rolling towards the center of the room. To me, it sounds like a lot. So this is your total long-term deflection here, which is the 2.176 includes your dead load and your live load, and then the 1.723 times the 1.286 is the additional deflection that you will see in another 5 years. So this is what you see on day 1. This is what's added over the next 5 years, so that 5 years later, this is your total deflection. Okay, so as I said, 4.39 inches of deflection. Does that sound good? Does that sound healthy? Question is that acceptable? ACI 318, section 2422, looks to table 24.22 for your deflection limits. For flat roofs, not supporting or attached to non-structural elements likely to be damaged by large deflections, the immediate deflection due to maximum of, that's rain live load, snow, or rain, your allowable is L over 180. For floors, not supporting or attached to non-structural elements likely to be damaged by large deflections, think glazing or maybe even drywall that's put up tight, if it's not supporting something that would be destroyed by some kind of deflection, then you can have an immediate deflection due to live load of L over 360. And for roofs or floors, supporting or attached to non-structural elements that are likely to be damaged by large deflections, that part of the total deflection occurring after the attachment of the non-structural elements, which is the sum of the time-dependent deflection due to all sustained loads and the immediate deflection due to any additional live load, that's a mouthful, but that allowable is L over 480. If it is not likely to be damaged by large deflections, then this is all the same statement, L over 240. So these are your deflection criteria. You have to kind of read through these and see which one you have and compare it to your, these are your acceptance criteria. So were the deflections of example 3 acceptable? To answer, we have to make some assumptions. If we assume that the beam in question was part of a floor with non-structural elements attached that are not likely to be damaged by deflections, then we must find that part of the immediate deflection that occurred after the attachment of the elements. This deflection can be assumed to be equal to the total minus the dead load. Why is it the total minus the dead load? Because when we built the beam and we kicked out all the shoring, it deflected immediately to delta D. That happened immediately. Then they called in the drywall guys. Then they called in the glazing guys. All the rest of the structure was built then to what was already there. So this deflection doesn't tend to crack the drywall or smash glass because those guys came in after. But any load that happens after this happens would tend to cause problems. So delta is delta total minus delta D, which is my total 4.392 minus the 1.063 inches that occurred immediately. I have 3.329 inches of movement. My allowable is L over 240, which is 36. I converted it to inches over 240. 1.8 inches is my allowable. Calculated deflections are not acceptable. 3.3 is much more than 1.8, not so good. We must also check the live load deflection. Live load deflection was 1.113 inches. My allowable is L over 360, which is 1.2 inches. So it actually barely made it. It was okay for the live load deflection. Okay, any questions about any of that? Okay, let's talk about cracking. Cracks are an acceptable fact of life with reinforced concrete. Basically, all reinforced concrete will crack unless very extreme conditions that it doesn't crack. Steel reinforcing doesn't even start to work really until the concrete has cracked. So cracks cannot be avoided, they must simply be controlled. ACI 318, since 2002, they no longer explicitly limit the crack widths of reinforced concrete. They no longer, I don't know what that is, they limit reinforcing spacing. They used to use as a guide the following values. So what they used to say is what a lot of us still follow. If the exposure category, allowable crack width. If you have dry air or a protective membrane, you can go as big as 16 thousandths of an inch. Humidity or moist air, soil, 12 thousandths of an inch. De-icing chemicals, 7 thousandths. Seawater or seawater spray, wetting or drying, which is pretty bad, 6 thousandths. Water retaining structures, where you actually want to keep the water, 4 thousandths. So we basically still follow this to this day. because the newer equations that they use in the code limit reinforcing spacing. It doesn't really work very well with beams. So to check crack widths, we can use the following expression. This is 76 thousandths beta h f prime s and the third root of dc over times a. This is known as, I can't even pronounce this guy, but Gurgely-Lutz equation. Oh, Garge. I'm sorry. I wrote that in there so I wouldn't mess it up, and I messed it up anyway. This guy is the Garge-Lutz equation, where W is the crack width in thousandths of an inch. Beta H is the ratio of distance from the neutral axis to the extreme concrete in tension over a distance from neutral axis to the tension steel. F sub S is the stress in the steel, KSI. You may use 0.6 Fy for simplicity, or you can calculate this explicitly. D sub C is the cover of the tension steel from the centroid of the steel to the extreme concrete in tension. And A is the effective tension area of concrete, equal to the area of concrete with the same centroid as the steel divided by the number of bars. Okay, so let's see, it's 5:50. I believe I have just this last example, and then we're done with this presentation. There'll still be plenty of time to talk about the midterm. What do you say we take a 10-minute break, reconvene at 6 o'clock? We'll finish this example, and then we can talk about the midterm. What do you think?
Perfect.
Sounds good.
All righty, great. Let's reconvene at 6:00. Okay, we are back. And looking at this final example, at least I think it's the final example. So here's our beam, very similar to the one we just looked at, only no compression steel. 27 inches deep, 20 inches wide, 6 number 8s. And we're repeating the last example to find the maximum crack width with dead load only. From example 1, which was last lecture, but from example 1, we know the beam is cracked under full loading. Therefore, we use the cracked moment of inertia. Solution. So we find the modular ratio is 29,000 KSI over 3605 KSI. And again, you can go back to example 1. I pulled a lot of the numbers straight out of there. Modular ratio is 8.04. Y sub B was 19.06, distance to the neutral axis. I cracked was 13,788 inches to the fourth. And M sub A is M sub D. We're looking at it at the dead load stage, 253.2 kip feet. So F of S we get from our flexural formula. Stress equals my over I. So M is M sub A, applied moment. Y is the distance to the neutral axis. N is the modular ratio. And I is for I cracked. Y sub B. Anyway, I was wondering about that number. Anyway, so you plug these in, you got 253, convert it from feet to inches, 9.06 modular ratio divided by the crack moment of inertia, you get 33.8 KSI. So again, we're nowhere near the final condition. The steel is basically a little bit more than halfway to the yield, but this is the condition of the beam under the full dead load. Okay, beta sub H is the neutral axis divided by the neutral axis minus the distance to the steel. So if the steel is 2.5 inches up, then you get 1906 minus 2.5. That's 1.151. And I just realized this is a typo right here. If you want to make a note of that, this is actually supposed to be 19.06 minus 2.5 to get to Y of the steel. So that's a mistake right there. In fact, I will note that in my notes to fix. Slide 415. Y sub B minus D. Sorry about that. Try to catch all these that I can. Anyway, does that make sense? Anybody have questions on what I just did? What I'm saying is Y sub B, this should be Y sub B minus 2.5 to get to the level of the steel, not the very bottom of the beam. Everybody okay with that?
So professor, from the central axis to the steel. That's why we do the minus 2.5.
Yeah. The
Okay,
neutral,
got it.
yeah, when you go back to example 1, we found that the neutral axis, this is 27, so the neutral axis is like right there. And the distance from the neutral axis to the bottom of the beam is 1906. So this should have been 1906 minus 2.5.
Got it. Thank you.
Okay. So sorry about these typos. They're embarrassing, but you try to catch them all. Okay, so, but this is correct here. Beta H is 1.151. D sub C is the cover from the bottom of the beam to the center of the steel. That's assumed to be the 2.5 as labeled here. And A is the weird one. A is an effective area in tension that has the same centroid as your steel. So if the center of my steel is 2.5 inches up from the bottom of the beam, then A is a band that's 5 inches tall. If I had multiple rows of steel, then A would be basically twice as high as the distance to the center of all your steel. So A is going to be 2 times DC high, or 5 inches high, times the width of the beam, and then you divide by the number of bars. So it's kind of like the effective area of concrete in tension per bar. It's kind of weird, but that's how they do it. So 2 times 2.5 high by 20 inches wide divided by 6 bars gives me 16.67 inches squared. So I put it all into my equation, Gerge-Lutz equation, and I plug in my 0.76, 1.151, 33.8 KSI, and the third root of 2.5, 16.67. And this all comes out to be 10.3. The equation gives you 10.3, but the equation is in thousandths of an inch. So this is actually 10.3 thousandths of an inch, or 0.0103. Actually, let me go back a little bit. So is this okay? Does that sound like this is okay? Well, if it's inside a building under normal circumstances, even right here, that's less than 12 thousandths of an inch. So generally speaking, yes, this would be okay. These are kind of more extreme conditions. Normally, we're trying to get between 12 and 16 thousandths of an inch. Just as a comparison, when you start getting cracks that are like 17 to 25 thousandths, that's when it starts getting a little concerning. You look at a concrete beam and you see a crack that's 25 thousandths of an inch wide, you notice it. You're like, huh, what's going on with that? You start seeing cracks that are like maybe 1/8 of an inch wide, that's when you should really start being nervous about even being in the building. And I've seen cracks that are over 1/4 inch wide, but that was just before the beams failed in a testing situation. ACI 318 now limits crack width by limiting the spacing of the flexural reinforcing bars. ACI section 2432 points to table 2432 that limits the spacing of reinforcement S to the lesser of, and these are just some prescriptions. So whichever is lesser of these two. And ACI section 24321 allows S sub S to be calculated or to be taken as 2/3 of Fy. And C sub C is the clear cover of the reinforcement. This ACI 318 criteria is actually much more useful for rebar spacing and slabs, not so much for beams like in our examples. You know, in our examples, the rebar spacing of the beam we just did was probably 3 inches on center. And these equations generally give you numbers like 9 to 15 inches on center. I really just don't get why ACI put these in here. They're practically useless for beam design. I think even the textbook, I mean, the guy that wrote your text is pretty polite. I think he even kind of alluded to the uselessness of these equations, but it is what it is. Okay, so do we have any questions about serviceability?
Professor, I had a
Yep.
quick question.
Sure.
So how about let's say since we got 0.01, how about if we got something bigger? Then how would you fix that as a designer?
Great question. I like that question. Okay, so look at all the variables that went into the Gerge-Lutz equation. Beta, F sub S, D sub C, and A. Beta, you don't really have much control over, and that's only 15%. F sub S is a big contributor. 33.8 KSI. You really don't want to be much higher than that under service loads. So what do you do about this? Well, you can put more steel in there is one thing you can do. More steel will lower this stress, or the moment of inertia also. So you could make the beam deeper. And that probably would be the most effective way to control this, is to make the beam a bit deeper and or add some more steel. But one important thing is, if you're constrained to a certain depth, so let's say this is the beam size, I can't change it. I have to be 20 inches wide. I can't go more than 27 inches deep. What can I do?
Won't you put compression steel?
Compression steel would help a little bit, yes, because it would add to your crack to moment of inertia, yes. But the tensile area down here is the area that's in the same centroid as the steel divided by the number of bars. So one thing that's really important as a designer, when you're figuring out how much area of steel you need, you're choosing to use either 6 number 8s, or you could use 5 number 9s, or you could use 3 number 10s, or you could use 2 number 14s. They all have the same area of steel, more or less. So as a designer, do you use 3 bars that are big, or do you use 6 bars that are small? What difference does it make? If you're having an issue with cracking, that's one thing that you can do that will really improve this, which I already did, by the way. I already have 6 smaller bars. But if you're trying to use, say, like 3 number 11s, 3 number 11s would produce much wider cracks than 6 number 8s, even if it was the same area of steel, because of this factor right here where you're dividing by the number of bars. So that's just kind of one of those universal truths of concrete design. Bigger bars result in bigger cracks. More smaller bars is better for crack control than fewer bigger bars. And I think that's an important takeaway from this.
Professor, if you make smaller bars, wouldn't that make your beam wider?
Well, I mean, within your allowable width, yes.
Oh, okay, makes sense. Thank you.
Yeah. I'm assuming you can still get 6 number 8s in the 20, but, well, let's see. Just for conversation, 6 times 0.79 was 4. So that's 5 number 9s. If I divide by 1.27, that's 4 number 10s, 0.5356, and basically 3 number 11s. So 3 number 11s or 6 number 8s have almost exactly the same area of steel. So for the same area of steel in the same beam, they all fit within the 20 inches. The 6 number 8s will do a much better job than the 3 number 11s in crack width because of this factor right there. Any other questions about this presentation? Okay. So what else do you guys want to talk about? What else is coming up down the road?
Midterms coming up down the road in 2 days.
Midterm. Okay.
Yeah.
All right, let's talk about the midterm. First thing is that you will have to use the Respondus lockdown browser. And I had assumed, absolutely incorrectly, I had assumed that all of you have used this by now, since we did this whole COVID thing halfway through the spring semester. I had to do a midterm and a final for my last class using Respondus. So I had assumed that we were all kind of used to it by now. But I found out that that is not the case. It is what the civil engineering department, okay, It is what the civil engineering department told me to do. So they gave me a, oh, what do you call it? A PowerPoint presentation on how to do tests on Respondus, and I've done it a few times, but I understand that some people have never used it. So here's the deal for Respondus. Let me get out of this real quick. Okay, so the first thing is you have to download it onto the computer that you plan to use for taking the midterm. So you do that beforehand. You download the lockdown browser, and you have to use, you know what? Oh, shoot, I forgot about that. I can do that while I'm talking, perhaps, maybe. I had a student last year say that she downloaded the lockdown browser and it couldn't find the test. And the issue was that she didn't download it through Cal Poly. She just went out to the net and downloaded a trial version of it. So you have to download the version that's like licensed to Cal Poly. So let me find this. Browser info. Pretty sure this was the one. And submit on that. Okay, so I just put the browser info on Blackboard, and this is what you get when you do that. So it gives you an overview video, and then you download the file. Now you have to download it from here. See, don't just go out to the net and download some random trial version copy. You have to download it from this link on this PowerPoint that I just gave you. And when you do that, if I got my facts right, it downloads the Cal Poly licensed version of the lockdown browser. And then when you open it up, it will find the midterm because the midterm's been linked to the download. So anyway, use this to download it. And then you go to Blackboard and okay, so everybody sees this. Everybody's got this part of it. Make sure you download Lockdown from here. And then you go to Blackboard. Sure, this might look a little different for you, but you go to Blackboard. My understanding is then you go to, was it Course Tools and Respondus, Lockdown Browser. And see, here's the test loaded up. Now, it's not letting me click on this yet because I set the test so that you can't start it before 4:30 on Thursday. So it's not live yet. But after 4:30 p.m. on Thursday, you click on this and you start the process. You hit begin and it starts going through what it does.
Professor, so we go through like our regular browser to the Blackboard, or we have to open the lockdown browser and go through that?
I think you download Lockdown Browser onto your machine and install it. Now it's on your machine. Then you go to Blackboard, find it under Respondus Lockdown. You'll see the midterm is there. You double click on the midterm and it opens up the midterm in Respondus Lockdown browser.
Got it. Thank you.
Pretty sure it's like that. Also, read the instructions that I just uploaded to Blackboard. That PowerPoint presentation has a lot more instructions on it. Okay, so we did this, like I said, we've done this twice now. And there were a few issues, and I will tell you about what those issues were. But the majority of the class was able to take the test, and it doesn't show up. I don't even know how to do that. Well, let's go back to Blackboard. So it's
You use it's under course documents, I believe.
well, course documents is where I just put that browser info. But the test itself, it's either under tests. See, here's the test. Or you go to under your course tools. Under the course tools, you should have a Respondus Lockdown browser. And from here, you see this screen, and this will be live when you get there.
Professor, I have course tools, but I don't have that segment of it.
Okay, then you probably have to, do you have, I created tests. Do you have tests?
Yes, I do have the tests. It's
And-
under the tools, but
and
I
you-
don't have that. I don't have that. No.
Well, it's hidden from students. It'll be available after 4:30. I think that's why.
So the link
Okay.
would be up after 4:30 on Thursday under tests.
Mm-hmm.
Okay.
That is my understanding, yes. The browser. Okay, so let me try to make this clear. Between now and Thursday, like tonight or definitely by tomorrow, you follow the instructions of what I just uploaded and download the browser onto your computer. It has to be installed on your computer because it takes control of your computer while you're taking the test. Don't do that at 4:30. Do that tonight or tomorrow, whenever you get a chance to do that. So once you have it installed on your computer, it'll look like this. Am I still sharing my screen?
Yes.
Okay, so if you can see just the icons, the Lockdown browser is on my machine. And then at 4:30 or after, you go to Blackboard and open up the test. And again, I'm not sure if it was from the Respondus, from the course tools, or you just go to tests and open it that way. One or the other is the way that you get in there. Okay, once you get to your test and you say begin, then what it's going to do, excuse me, you have to have something with a webcam. This will not work if you don't have a webcam. So you have to have a laptop that has a webcam built into it, or you have to have an aftermarket webcam that you plug in with a USB. Either way would work just fine, but it has to have a webcam. So you set up your area where you're going to do your test, take everything off your desk because it's going to ask you to sweep around and show me what's on your desk. The only thing that you can have on your desk when you take this test is your textbook or pages from your textbook's PDF that you have printed out. So either print it out or the actual textbook itself on your desk, a pad of paper that you can use for working through the problems, and your 1 page of notes, and then a calculator and a pencil and whatever. That's it. Most importantly, what you may not have on your desk is another computer, another laptop, an iPad. Obviously, your phone cannot be anywhere near your workstation. You cannot be sitting there and playing on your phone while you're taking the test. It will definitely flag for that. And I don't know if you're talking to your grandmother or if you're getting all the answers to the test. So if I see anybody with a phone during the test, that's considered to be a compromised test. I want to make sure I'm very clear about that. And this thing's watching you the whole time. So do not pull out your phone unless you have to text me. Now, if you're having some kind of a major catastrophic, everything's falling apart, then you text me. My phone number is 909-342-2797. So if everything is falling apart, text me, and I will know who texted me because I have my phone, and then I'll see the respondus recording, and I'll see somebody playing on their phone. If they're the same person at the same time, then that would be okay. Any other reason, it basically is a disqualification of the test. So I want to make sure everybody is crystal clear that it is watching you the whole 2 hours, and if it sees you with a phone and you're not texting me, that's a compromised test. Okay, can I hear some howdy doodies or
Professor,
understood?
understood. But Professor, would you repeat the phone number again, please?
I will do it this way. Okay, so hopefully everybody can see that on their chat. That is my cell phone number. Do not harass me at 2 o'clock in the morning, but you can text me during the test if you're having catastrophic failures. This has happened, I think, maybe to 2 students at a time, where one student had an internet interruption. Once there was an internet interruption, it basically closed out the test, and they were only partially done with the first problem. So they were unable to complete the test because it basically canceled them and submitted the test with just very little work done. So what they were able to do is finish the test on paper, text me immediately, tell me what happened, and then we were able to upload that paper, and I was able to give them credit for what they were able to do. So that's an example of if something just totally is falling, all the wheels are falling off the cart. My internet does it and there's nothing. I would go to Panera or go someplace that has better internet, because if your internet goes out while you're doing the test, it will shut you down. That's the one thing you need to make sure is you have a reliable internet for this thing. Yes. Immediately text if something happens that basically locks you out. Okay, so let's talk about the test itself. Oh, I'm sorry, I'm jumping around a lot. Once you get into the system, what it's going to do is make you stare into the camera, and it looks at your face. Then it makes you hold up an ID card and hold up an ID card, Cal Poly identification, your driver's license, something like that. And then it has you sweep around looking at your desk area, make sure it's clear of anything that would not compromise your test. And then you can start working on the test. What you're going to find once you start working on your test. There are actually going to be 4 problems. Each problem is its own PDF page. So you open up the PDF, and that is that problem 1, 2, 3, or 4. And then under that, you're going to see a text box, like an essay type answer. What I want you to do is to type in to the text box the actual answer. So if the question is, what is the allowable capacity of such and such beam? You would type in for problem 1, part B, the answer VMN is equal to 342 kip feet, whatever. But type that in. And so you're going to have for every problem, every part, problem 1, part A, problem 1, part B. There's one text box for problem 1. So you're going to put a part A, type in the answer. Part B, type in the answer, so on and so forth. Answer all the questions with that text box. When you're finished, or you run out of time, whichever comes first, when you're finished, you hit submit, and the whole thing goes into the Blackboard system for me to grade. As soon as you submit, whether you ran out of time or you voluntarily hit submit, either way, as soon as you are done, then what you do is all the work that you did on a pad of paper, scan that along with your 1 page of notes and send that. You don't send it to me, you upload it to the midterm assignment. Okay, so there's a midterm test and there's also a midterm assignment, just like homeworks. It's an assignment. It's worth 0 points, but it's a place for you to upload all of your work so that this weekend when I sit down to grade these tests, if 1A, if the answer is wrong, 1A could be worth 10, 15% of the whole test grade. So if there's no work that goes with it, then if that answer is wrong, I have no choice but to mark you down for all the points that were associated with part A. Part A might have been, like I said, part A might be 5 points out of a 50-point test. But then you upload your work. So if part 1A is incorrect, I can go through your work and say, oh, all right, well, that was correct, that was good. There's one mistake there, -2 points, and this is okay from there. See, so I can give out a lot of partial credit looking through your work to see what went wrong, as opposed to just grading straight from the text boxes, which would be very difficult because everybody would basically have to get perfect answers. Does that part of it all make sense?
Yes, thank you.
Professor, when we're scanning, I know some of us use a phone app to scan to PDF.
Yes.
How would we go about that if we're not going to be using phones?
No, that's okay.
That's
Because
okay. Okay.
no. And Victoria basically had the same question. No, what you're going to do as soon as you hit submit, then it's going to end the test for you. And as soon as it ends the test, it stops watching you. It's not recording you picking your nose or whatever you're doing. It's not recording that anymore. And from the moment you hit submit, I really don't know what you're doing. But you can hit submit, it loads up your test is done, and it gives you your computer back. It's no longer locking you out of all of your apps. So it gives you your computer back. Once you have done that, you can use your phone, you can use your scanner, you can use whatever you need to use to scan your work and upload it into Blackboard. I'm just asking, do that in a reasonable amount of time, 15 minutes or so from when you finish, upload that work. I don't want to see it coming up 2 hours later when you've had time to go through and redo everything, right?
Right. Okay.
But you know, within a reasonable amount of time, give me all your work in your 1 page of notes, and I will do the best I can to find if and where you've made some mistakes and give as much partial credit as possible.
Got it. Thank you.
Okay, great. Oh yeah, that's the other thing that the lockdown browser will do. The lockdown browser locks up your computer. That's what it does. So while you're taking the test, you will not have access to the internet. You will not be able to Google anything. You will not be able to bring up your PDFs of your textbook or anything else for that matter. So please make sure that whatever you need for the test, that comes from the textbook. The textbook is the only book that's open book for this thing. So if you do not have a physical textbook in front of you, you make sure that you print off whatever you think you're going to need for this test. Garrett, have you posted what tables we need to print? No, basically the test assumes that you have your textbook, and whatever tables you will need will be in the textbook. So if you need all of the tables in the appendix, print those out before this test. If you need chapters 1, 2, 3, and 4, print those out before you take this test. That's what I'm saying. It's kind of up to you to print out whatever you think you're going to need for this test and have that printed copy with a big clippy on it or a big staple or whatever, and that's your textbook. You could print out the whole textbook. Yeah, absolutely. And just have it bound or clipped or something so that when you look around and I see this big giant pile of papers, I know that's your textbook. Yeah, exactly, Ashley. You can print out the whole textbook or the chapters that you think you need or just the appendixes, whatever you think you need, print that out and that becomes your textbook. And then you still have one page of notes that you can write. For example, if you're afraid you're going to freak out and forget the moment due to a uniform load on a simply supported beam, which is WL squared over 8. If you think you're going to forget that, write that on your page of notes. How do we show you in advance? When you start the process with Respondus, when you hit begin, one of the things it's going to do is have you pick up your computer or your webcam, whatever it is, and kind of sweep around your workstation. And I'll see that big pile of stuff on the middle of your desk. That's your textbook. That's how you show me. Okay, so that's kind of how the whole thing works. Again, you have my number. Text me if you get kicked out or it shuts down on you or whatever. If I get 32 texts at 4:45, then I'm going to know that nobody's being able to get into it, and I will jump on this thing and try to figure out what the issue is. The way that it works, by the way, is that as soon as you begin, you get 2 hours. So if you're having troubles and you're getting frustrated and you're freaking out and you don't actually start the test until 5:20, well, you get 2 hours from when you start. Okay, so don't freak out too much. I think I set the limit that you can't start it after 7 o'clock, but there's plenty of leeway between 4:30 and 7 to get started. And then once you start, you get your 2 hours. Okay, does that make sense to everybody?
Professor, just one thing here. It almost seems like it wants us to be robots. There's a part here on the PowerPoint where it says students pick up unusual objects like notes, paper, which you know, if we print out the textbook, we're gonna be flipping back and forth.
Yes, you will.
It's gonna capture, software's gonna capture the moments, and it will report it to you.
Yes, it will.
Okay.
Yes, it will. But don't worry about it. What it does, like I said, I've gone through this several times now. What it does is it records you for 2 hours, but you'll forget about that. You'll totally forget about that. And almost every single student gets flagged somewhere between 20 and 40 times. It flags you if you look down at your paper. It flags you if you sneeze. It flags everything. So basically what it is I go through and I go from flag to flag to flag to flag. And I just confirmed that you didn't pick up a cell phone or you didn't disappear and come back 5 minutes later with all the answers. That's all it's doing. So really, like I said, once you get started and you start working on it, it's going to be like any other exam that you've ever taken in class. When you take exams in class, you know I'm watching you, I'm watching everybody, but you forget about that. You don't worry about that while you're taking the test. And you're going to forget that this thing's even watching you after a while. I know that from hearing what people have said, so I know that happens. But just don't do anything that you know you shouldn't do, and you'll be fine. If you like, Ashley, as long as I can see that. As long as it doesn't kick you from the test, you should be good. That is correct. If it kicks you from the test, then you got problems, and that's where you need to text me and we need to work it out. But like I said, I've given this test twice now I had 37 students, so that's, what is that, 74 test takers. And I think I had 2 issues that we resolved during the test.
Will you still have office hours at 4 o'clock on Thursday?
Yeah, I can. I could do that.
All right, thanks.
And then after office hours, I mean, after like 4:30 or so, I think people are going to try to start taking the test and get it over with. So after about 4:30, basically I'll just be sitting on my cell phone, hoping that nobody texts me and tells me something horrible happened. But I'll be sitting on the cell phone ready to respond if I have to.
Sounds good. Thank you.
Okay. It's going to record noise. Do we need a mic to be on? I don't think you need it to be on. I think just most laptops, it just does that. Yeah, I mean, doesn't need to be on. When I review it, like Eric just said, he'll review the footage, see what is cheating and what is just us going through our notes. It does record sound during the testing, yeah. And I've heard some pretty funny things from people who forgot it was on, but that's fine. Let me talk about the test itself for a minute, as opposed to how Respondus makes this all different. But the test itself, I do my tests a lot like the homework, except that I don't ask for everything that I ask for when I do the homework. When you have the homework, you have more time to go through things and make sure that you understand how to do every step. But during the test, we don't have the luxury of time. So please read every question carefully and make sure that you give me everything that I have asked for. But by the same token, do not give me a whole bunch of stuff I did not ask for. Classic example, if I ask for the allowable capacity of a beam, I'm asking for phi min. Phi min is equal to something. So do not do a shear diagram and design a whole bunch of shear ties. I didn't ask for shear design. I only asked for phi min. So as you're going through, please read the questions carefully. Take a minute, understand what it is I'm actually asking for, and just give me that. Don't give me, give me supporting work that gets you to where you need to go to, obviously. If I'm asking for phi min, then there's steps that you get to there. If I'm asking you to design the steel in a T-beam, there are steps that get you there. But don't go off onto shear design or deflections or something totally different that I didn't ask for. The other part about my tests is you have to manage your time. You got 2 hours, you got 120 minutes, but manage your time. It is far better to give me 95% of all 4 questions than it is to give me 105% of one question and 5% of the other 3. You will not do well if you spend all your time on one question. So please read the questions carefully and manage your time. Well, the questions should be very self-explanatory. So hopefully you won't have any issues understanding it. I went back through, redrew some of the diagrams so that they are clearer. All the information you need should be right there in front of you on the test. If there is something that you think is just totally missing, and there may be, I may have just totally blown it and forgot to tell you what the grade of steel was or something basic. If there's something missing, then write down on your work, this is missing. I will assume this. So, professor, you forgot to tell us that what F prime C is of the concrete. So I'm going to assume 4,000 PSI and then work the rest of the problem from there. And you'll do far better than just freaking out and don't know what to do. Okay, so we still got 14 minutes. I will just leave it up to questions then if you guys have any more questions.
Professor, I had a quick question. So for example, let's say you ask us to find the FMN, right? But are you gonna ask us like directly, or find AS min, find the ET, make sure it's bigger than 0.005, or does that come with the question of get the FMN?
I tried to do a pretty good job of being specific about check your minimum, check your maximum, check epsilon sub t, justify phi might be a way that I say it. But if I flat out don't ask for it, then you don't need to do it. So in other words, if I flat out do not ask you to check that the steel that you have will fit into the beam that I gave you, then don't worry about it fitting into the beam that I gave you. Garrett, that is correct.
Thank you.
Shayna, are we able to text you with questions about the exam, or you'll answer respondus issues? I was thinking about that very question, but I think it is better that you do not text me with questions about the exam. If something is not clear, make an assumption and document that assumption. Professor, you're a doofus. You forgot to tell us how deep the beam is. So I'm going to assume 30 inches and go from there. Because the problem is, if I have 32 students texting me with all these different questions, there is no way I am possibly going to be able to correlate that back to every time the respondent made a major flag that somebody's using a cell phone. So let's keep the cell phones just for catastrophic failure. And that would keep it a lot simpler. The chapters, I'm not sure exactly which chapters they are, but they are from chapter 1 through T-beams. We are not covering compression steel, but we are covering everything from chapter 1 through T-beams.
Professor.
Yes.
So it's safe to say that roughly 95% of the points we earn are gonna come from the work we submit through Blackboard rather than the final answer we submit during the respondus?
Not necessarily. If all of your answers are correct, then none of your credit is coming from your uploaded work. But if all of your answers are incorrect, then all of your points are coming from your uploaded work. Does that make sense?
Right. So if it's correct off of respondus, you don't bother looking at the work. You sort of just you move on to the ones that were incorrect, or
no. That's a very good question, but no. If all the questions were answered absolutely perfectly on respondus, I am still going to go to the work to make sure that there is work. Or otherwise, I'll be very suspicious as to how somebody was able to get all the right answers with no work. See what I'm saying?
yeah, right on.
Okay. And so I'm going to work the two together. So even if somebody had absolutely 100% perfect paper I'm going to make sure that the work reflects those answers. And most of the time, most people get a lot of the answers good or close, but they got some problems here and there. And that is where the work really, really will help you, because I can isolate exactly what the problem was. Garrett, no, nobody mistook a calculator for a cell phone. That didn't happen last time, so that's okay. Ashley, we will not cover doubly reinforced beams because that's compression steel. And the exam is covering lectures 1 through 6. I can't say that at the moment. It's where we talked about T-beams, and we had T-beams analysis, and we had T-beams design. All of that is on the exam. But then we moved to compression steel or doubly reinforced. That's where we draw the line. That is not on the exam. Okay. Any other questions?
One last thing. How do we go about restroom breaks?
That's a good question. Yeah, somebody asked me that just a little while ago. That never came up last time. Nobody ever had to pee in the whole test. 74 test takers, not once did that happen. I was going to suggest that if you have to take a restroom break, then take a piece of paper or your sheet of notes or whatever you're working on and write restroom pass or hall pass, or let's go back to grade school here, hall pass, and show it to the camera. But the important part is when you go to use the restroom, if this comes up for you, do not take anything with you. Don't take the work that you're working on. Don't take the tests. What, you know, obviously, right? But just show the camera that, you know, I need to use the restroom. Get up, use the restroom. I expect you back within a few minutes, and continue with your test. Don't take your calculator. Don't take your book. Don't take anything with you. And I think we will be okay. Cheat sheet, 1 page front and back. I'm thinking 1 page front. The back of these papers is completely unreadable. So even if you can read it, when you upload it, I can't read it. So just the front. And by the way, I still got 8 minutes left here. Do not do any of your work on the back of engineering paper, please. Cheat sheet does not need to be on engineering paper, but you should do your work on engineering paper that you're going to upload. Okay, so, but back to my rant. Back to my soapbox. Don't do work on the back of an engineering piece of paper. I cannot read that at all. The next time somebody does that, I'm not giving them any credit because I can't read it. When you PDF that and you bring it up into Blackboard and try to open it up, all I have is a massive grid. I can't read anything.
Professor,
Yes.
but you told us that since when you make it one, like, you know, 1 page, only front, everyone writes very, very small. So last time we asked you, you told us that it's okay if you write big and put it on both sides.
I did, but I think I'm changing my mind because since then, certain unnameable people have uploaded their homework and they wrote on the backside, and I couldn't read it.
Thank you, guys.
Yeah. So I'm laying down the law. No backside of paper on nothing. You can use A4 white paper. Yes, you may. The cheat sheet can be on any 8.5 by 11 piece of paper you want. The work that you're sending up should be on green engineering paper on the front side only so that I can read it. the next time somebody submits homework written on the backside of homework, I will just completely ignore it altogether. Does not count at all. Okay, so hopefully everybody's clear about that. And I had a wonderful time this last weekend trying to read homeworks that were on the back. My scanner always turns the paper white and black. That's fine. That's fine. Just don't do it on the back where the grid is so dark that you can't see anything. All right. And somebody had a question that I haven't answered. Jesus, I've noticed that we've had problems with lightweight concrete. Would it be covered later, or should we jot down the density of lightweight concrete? You do not need to jot down the density of lightweight concrete, because if I give you any problems with lightweight concrete, I will tell you what the density will be of the lightweight concrete. And oh, by the way, if I don't say anything about that, assume normal weight 150 PCF concrete. Okay, Garrett, yeah, I don't see the grid when I scan. You can do whatever you want, but if you send me something that I can't read, I'm not gonna read it. How about that?
Professor, since you
Yes.
said there's not going to be any double reinforced beams or anything with double reinforcement, does that mean whenever we're finding the ICR, does that apply for that too? From lecture 2, does that apply to those double reinforced beams too?
Yes.
Okay, thank you,
Yes.
Professor.
Yes, that does apply to that too. And by the way, whatever from chapter 2, which was M cracked, modular rupture, and cracked moment of inertia, you may see it on this test, you may not see it on this test. I'm just saying that's within the scope of this test. But those topics played very heavily into the lecture we just finished. And the lecture that we just finished was the real end goal of those topics, which is to get deflections and cracking. Deflections and cracking is not on this midterm, but it will be part of the scope of the final. Ashley, yes, you take your cheat sheet and you put it with all the work that you've done during the test, and you scan and upload all of that to me.
Professor, for the cheat sheet, can we write general steps on how to solve certain parameters, or do you want, because I know we can't put examples, so.
No, that's a very well thought out question. Yes, you may write down procedures. I even, in fact, I remember in one of the slide presentations, I wrote down for you kind of like a step-by-step procedure. That's fine. Well, what I'm trying to avoid is actual written out examples. So I don't want you to copy an example that I did in class. I don't want you to copy a homework problem. Really, the issue is test security, and so I've had problems in the past of people writing out full-blown examples on their cheat sheet, and then when you actually look at the cheat sheet, it's actually like from a midterm that I gave 3 years ago or something like that, and that obviously is a compromise. So that's why no examples, but writing out a step-by-step, if you want to write something to the effect of T-beam design, okay, assume it's rectangular, step 1. Step 2, solve for A. Step 3, is A thicker than the flange? Yes, it's a true T-beam. Step 4, start over, find the capacity of the flange, take it away from MU, solve for the balance in the web, blah, blah, blah.
Okay, thank you.
No, I had a question that said the test will cover everything until last week's lectures. No, that's not true, because the test will not cover doubly reinforced compression steel, and I think that was more than a week ago. That sounds about right. Again, I don't know exactly where in the book that is. I don't know exactly which lecture that was, but compression steel will not be covered. All the T-beams and everything before that will be. Okay. Okay. I cannot either agree nor deny that allegation, but it sounds about right. All right. So again, on Thursday, I will have office hour till about 4:30. The test will be available at 4:30. The idea is that you take it from 5 to 7. If you have issues, not to worry, you can start it a bit later and you can finish it a bit later. You still get your 2 hours. And if you have issues, not even be able to get into the test, then text me and I will get into Blackboard and see if I can resolve it. But first, make sure you do all the instructions from that PowerPoint, download your browser, all that, make sure all that's done beforehand. And then if you get into and you start taking the test and the power goes out, the internet goes down, whatever, then text me and we will try to work through it. So I think I'm going to end it now if there's no more questions. And good luck to everybody on Thursday.
Thank you, Professor.
Thank you.
You're welcome. Ashley, yes, that ID and show screen stuff is for the test.
Professor, I'm sorry. Are we able to resubmit homework 4 if we already submitted one?
Resubmit? No, the system doesn't allow resubmitting.
Oh, okay. Is it okay if I email it to you? Because I forgot to put one last part for the last problem.
I'm really starting to, I've allowed it a few times. I really don't want this to be a habit because when I go through the grading, it's very hard to remember who sent what and what's the latest.
Oh, it's okay then. It's just the allowable capacity for the last part. I didn't put it in.
Go ahead and send it, and I'll try to remember to look at it. How about that?
Thank you.
Okay. All right. I'll be ending it. Thank you, everybody.